This is a tutorial that I wrote with a few other people who are also in the LZ Dark Matter collaboration, which is what I work in, Micah Buke and Reed Watson. This is sort of a more basic tutorial. It assumes that you know a little bit about machine learning, so you know the basic concepts, and you're specifically hopefully familiar with two simple machine learning algorithms: the boosted decision tree and the multi-layer perceptron, or a regular neural net. If you're not, you should still be able to go through it reasonably well. But the main point here is to be complementary to a bunch of existing tutorials that aren't specific to physics. So for example, TensorFlow has a bunch of nice tutorial material, but it doesn't cover physics specific things, and it's really focused on the API of TensorFlow specifically. So the goal here is to go through a lot of the different steps that will be present in pretty much any machine learning analysis, and to provide a working code base that you can use and start from. So let's see.
So as of now, the poll for whether or not you can access the collab should be active.
Great. I do indeed see the poll. So let's see if other people can answer the poll. And Chloe, can you just check it and see if we have people who are unable to do that?
And I posted the link to the collab. That should just launch it.
That's right. It should launch it for you.
Chat.
Should be quite simple.
As of right now, 100% of our answers are yes, but we don't have everybody in yet.
Yeah. Okay. Perfect. Yeah. We don't have to wait to have everyone. We'll just leave the poll open. But that's good. Should work just clicking a link. We might run into more technical issues as you try and run the actual cells here. We actually have Reed Watson is going to be one of our organizers who is on the call now, and he can also help answer technical questions. So if you run into something as we go through this that's not working on your version, if you make a comment, make a question in our Slido, he may be able to address it. He'll be watching that as we go through. Okay, so let's go ahead and get started on the material here. So this is a simple example. Oh, by the way, just quickly about the packages used here. So here we use the scikit-learn Python package for boosted decision trees. We use TensorFlow 2 for neural nets, and there's also XGBoost, which is a standalone package that does boosted decision trees quite well. My general comments are that scikit-learn is nice and that it has the widest variety of machine learning algorithms, and it's pretty nicely documented. And maybe more importantly, it has a lot of what I'd call helper functions, things like train, test, split for your data, that are convenient, even if you're actually doing the machine learning in a different program like TensorFlow. And then TensorFlow is very good for most modern deep learning, so all kinds of advanced neural net architectures, basically. So I wanted to take a real physics example instead of using, if you looked at these, any of these machine learning tutorials that are available for different packages, a lot of them focus on the standard MNIST data set, a bunch of standard images. And I wanted to make this a physics example. So it's important to have some intuition about the data that you're looking at and how to investigate this. So I just wanted to give a very brief introduction to the physics of the data we're looking at for those who maybe aren't familiar with it. In this particular case, we're looking at some simulated data for the LUX experiment. LUX is a liquid xenon time projection chamber, and it's a dark matter experiment. And the way data looks in such an experiment, if you're not familiar, when a particle, so it's a big tank of liquid xenon. When a particle comes in and scatters off of the xenon, we get two things happen. There's an initial flash of light that's called the S1, and that's detected by PMT arrays at the top and bottom of the detector. And then also free electrons are created, separated from the xenon atoms, which then drift in the presence of an electric field near the top, where they then produce a much larger flash of light called the S2 at the top. And that happens in what's called the extraction region, where there's a much larger electric field. So at the end of one of these events, the quantities that the typical reconstructed quantities you can get are the XY position, which you can get from this S2 hit map. So you can see this dark red PMT is around where the event happened in the plane. There's the depth in the detector, that's the Z position, which you get from the time it takes for the electrons to drift between to the top of the detector, which is the time between the S1 and the S2. So drift time and Z are sort of synonymous. And then there's the size of the S1 and S2 pulses. So we call them S1 and S2 area. And then another important piece of physics here is that there are sort of two main types of interactions in a liquid xenon or a liquid argon detector. There are nuclear recoils, where a particle bounces off of the nucleus of a xenon atom, and then electron recoils, where they bounce off of one of the electrons moving around. And the main important difference between the two is that these nuclear recoils, which are closer to a WIMP dark matter signal than our backgrounds, they have a lower ratio of charge to light energy. So that means the S2 to S1 area ratio is smaller for these nuclear recoils. So that's going to be really key in our data. We're going to be looking sort of at S1 and S2 sizes and the ratio between the two, and that will provide us with a lot of useful information. So in this particular example, we're considering a toy case of distinguishing two common calibration sources. So one is tritium. I abbreviate it CH3T because it's actually tritiated methane, so that's the chemical symbol for it. These tritium events are electron recoils, which mean they're background light. And then our other calibration source is DD neutrons, which are, so it's a neutron generator. And these events are nuclear recoils. So the DD is kind of similar to a WIMP dark matter signal. So it's kind of like looking at WIMP dark matter versus our backgrounds. Okay. And for our organizers, do we have any questions in the live session yet?
Not yet.
Okay.
But people can also, just as a reminder, post questions in the Q&A part.
Yeah. Okay, so let's go ahead and start actually running these. So the first cell, if you're not familiar, you can run a cell either using Shift-Enter, and you'll get a little warning saying it wasn't authored by Google, which is fine in this case. You can either hit Shift-Enter or you can hit the play button, and both of them will run the cell if you're not familiar with Jupyter Notebooks. So in this case, Google Colab is running on the cloud. So it's got its own set of packages. Here we want to install a particular package that it doesn't have by default called uproot. So you have to run this cell for that to work. And for me, it took a little while to get started. but now it's, okay, now it's done evaluating. I also have some commands here. If you wanted to run this on your own machine at home, you would have to install some of these packages here. But we won't go through that. So now let's go through the first step, the first main step of the tutorial, which is loading our data. And because there are plenty of examples of reading data in Python native formats, I wanted to get an example of reading data from the root file format, which many of you are probably familiar with. It's quite common in particle physics. So here we have a couple of data sets that are saved into a root file. Our tritium and DD calibration data are saved in a root file. They're in a tree called Nest because they're created by a program called Nest. And I just make a comment here, which is that these initial steps of compiling your training data set and applying cuts, you will probably in practice want to do that separately from the rest of the machine learning, because that might take a while and you wouldn't necessarily want to do it every time. But we just go through it here to be as complete as possible. Okay, so we then go to the next cell here. We have a few imports. Here we define in our root file what are the names of the branches that we want to read in, and these are the names of the variables for the data that we have. So you can see we have S1 area, S2 area, drift time, which is synonymous with Z, X, Y, Z, and then also there's a reconstructed energy. And I also define a few variables that we'll use to make cuts. So I prevent events from being having too long drift time, which means they would be at the bottom near the cathode, and from having too large of an S1 value. Okay, so now the next step, because this is running on Google Colab, the data isn't there to begin with, so you have to do this extra step of downloading the data from the GitHub repo. So make sure you run that, and you should get something that that looks like this. So now this data should be stored in our local Google Colab versions on the cloud. So then the next step, we want to actually do the reading in of the data. So there's this package uproot, which I described, which is a very nice Python package for reading in root data, especially if you're familiar with Python. It makes it very easy, I would say, compared to pyroot, which is another way to read Python or read root into Python. So when we run this, uproot will read this root file in as a pandas data frame if you do this step here where you say .pandas.df. So then we can see what variables are available in our data set: XYZ, drift time, S1, S2, energy. So those are the ones that we explicitly told it to read in. Then we apply a few quality cuts. We make an extra column in our pandas data frame, identifying these as class 1. That means signal-like. And then in this particular example, I only take the first 10,000 events after cuts. And I do that for both sources so that we have the same number of events of both types. In general, though, and this is sort of mostly just to keep things fast, in general, more data will mean the possibility for better training. So you don't generally truncate your data set. Then we do the equivalent thing for our tritium data set. That code is basically a copy of what's above. And then we combine the two. There's this there's a step here which shuffles it. So just in case the data were ordered, we wouldn't want to keep track of that information. That would potentially be cheating if the algorithm trained in a way that paid attention to the way that the data was ordered. And then we also can do some simple transformations on the data. So in these experiments, it's common to, instead of look at S2 area, the raw S2 area, you might take the log of the S2 area because it covers a broad range of orders of magnitude. And then you can also define the radius from the X and Y positions. So let me pause for a second here. So that's sort of the reading in the data section. Do we have any questions so far on the live questions feed?
I had one brief question because I'm not familiar with uproot.
Yes.
Does it only load as Panda frames, or can it load into NumPy arrays, which I'm, again, more familiar with?
Oh yeah, absolutely. So so this step, you can turn it into a pandas data frame. You can very easily turn the pandas data frame into a NumPy array as well. I think that I'm pretty sure you can directly have uproot to turn the result into a NumPy array. But if you can't, you could just add another line under here. That would be, you know, ch3p array equals np dot array ch3p data frame, for example. And then, yeah, and then this should be a NumPy array object.
Just to add to that, while people add any other questions. So uproot actually gives you something called awkward array back. So this can be converted to NumPy or pandas or whatever else. But the way in which root gets called, where you can have things embedded into one another, is actually more complicated, like a more complicated data structure than pandas supports, because it's non-tabular. Anyway, long story short, so it can do NumPy, pandas, but if you have like really complicated embedded data, check out awkward array within uproot.
Yeah, that's a good point. And oftentimes, you know, in particle physics, we have data structures that are not so simple. You might have nested arrays within arrays, for example, is a common use case. So these awkward arrays can really be helpful for that sort of thing.
Do you want to just load up the questions? I don't know if you can alt tab it. So you have a few now.
Ah, okay.
People can upvote whichever ones they like.
Let's see. Is uproot efficient if we analyze gigabyte or terabyte size data? So I think one thing, if you really have a lot of data, one thing that's common to do is not to read it into memory all at once, but to sort of read it in batches. I don't think uproot directly supports reading in through batches. I don't know, Chris, if you have a comment on that.
So there are ways of doing it out of memory with uproot, but I would recommend you check out the latest PyHep, which was a few weeks ago, where there's a tutorial on uproot and also more information on it.
So DD, that's an easy one. DD is short for deuterium because the way the neutrons are created in this neutron generator involves deuterium collisions, basically. And would the ordering of the data only matter in the case of a network using a recursive learning model? So when you do recursive learning, that's usually you explicitly give it some ordering, like a time ordering. That's not necessarily the same as the index ordering in your data set. So in principle, the ordering, the indexing of the data shouldn't matter, but you might, for example, have an algorithm that samples, when it's doing the training, it might sample the first batch of data from the beginning of the data set, and then the next batch of data in index order. And if it does that, and your first examples have some particular pattern to them, that might change the way that the training happens a little bit. And then someone asks, are questions archived for searching in the future? So they are archived. Chris, do you know if they get, if the audience can view the archive?
So I think it spits it out as a Google sheet or something like that. We'll try to remember for the end of the workshop. If we don't, just ping us.
Okay. And there's also maybe
you see there's an archive button, so it is archived somewhere.
Yeah. Okay, and then there's maybe some person got a technical error. Maybe Reed, if you could see about following up. If anyone else got the same error, please make sure to upvote that comment. And Chloe or whoever else is watching, if there are a bunch of upvotes, let me know and we'll stop that. Okay, so now let's move on to the next section. We've loaded in the data, only took 30 minutes. So now we're going to take a look at the data. We're going to visualize the variables that we have in our data set. So the ability to visualize the data nicely is a luxury that you have when you're looking at fairly simple physical variables like what we're describing here. Often when you're doing deep learning, your inputs are something like the PMT waveforms or something like that. So PMT waveform at time sample 3 isn't particularly physically meaningful. So you have to work a little bit harder in those cases to visualize, to understand the structure of your data and think about it properly. But I guess the point of this is that it's crucial when you're doing a machine learning algorithm to understand what the useful information is and how to give it and how to ensure that it's being used properly. And in some cases, you don't necessarily know going into it what the useful information is, and you can actually use machine learning to help you learn that. We'll discuss that a little bit here. So this next part, I do some plotting using the Seaborn package. It makes some nice, pretty plots. You could equivalently make all of these plots in Matplotlib, and later on in the tutorial, I do, in fact, do that. But essentially, it's just doing this pair plot step, which takes the variables, pairs them up, and then draws their distributions. So if we look at the legend here, we can see our tritium, that's sort of our background-like electron recoil source, is in green, and our DD neutron recoil or nuclear recoil is in orange. And our typical analysis space for a dark matter experiment would be in this log 10 S2 area versus the x-axis here is S1 area. So these are our charge and light signals. And you can see they're fairly nicely shaped, nicely separated, I mean. The DD, this Argentina-shaped orange blob, is pretty well separated at lower log 10 S2 area for a fixed S1 size. And then we can also look at the histograms, the distributions in 1D. You have to be a little bit careful when you're looking at this particular way of visualizing the data. It smooths out, it basically, it uses something called a kernel density estimator to smooth out the distributions. So they're a little bit smoother than if you histogrammed, and they're maybe a little bit less sensitive to binning, but it's not too precise. So this is just a way of taking a quick look at the data and seeing what information is there. you can see that in drift time, that's our depth in the detector, the distributions look quite similar. And that's because in our simple example here, our simulation just has them simulated uniformly throughout the volume of the detector. And in fact, a decalibration source wouldn't do that. But so that would be something that we would want to check in our simulation if we wanted to be representing the real calibration source. In our case, we want it to represent WIMP data. So it's actually more representative of what we want. And there's also the radius. And then you can see if you look at Z versus drift time, it's a line with no spread here. So that is a quick indication that the two are actually one-to-one related. In real data, they're not a perfect, there isn't a perfect translation. So another thing we can do to look at our data is just look at the linear correlations between the inputs. You can do that by just, when you have a NumPy array, you can just call this core method, and it will get the correlations, and then you can draw it as a heat map. There's some notes here on different correlation coefficients, but it's important to remember that this is only a very blunt instrument. It tells you sort of linear correlations, but if things are correlated in a more complicated way, it won't capture that. So you can see very clearly that log 10 S2, S1, and reconstructed energy are all positively correlated with each other. And that makes sense. At higher energy, you just get more light and more charge. And then the position variables are more independent of each other. The radius and the drift time are independent of each other, but Z and drift time, you can see they're actually perfectly anti-correlated. So when we have this case where we have two variables that are perfectly anti-correlated, there's really no value in having them both fed in to our machine learning algorithm. So the next thing we do is we remove the drift time, and we also have this reconstructed energy variable, which in this particular case, the simulated resolution is sort of unrealistically good. So we want to actually take it out because not because it's not a useful variable, but because it's not representative of what we would see in our real data. And you can try on your own if you want, commenting out this line and seeing how well the next steps will do. They'll get almost perfect discrimination when you leave that in. Okay, do we have any live questions? Okay, the diagonal graphs in the visualization part. So that these diagonal graphs are just histograms, essentially. They're smooth histograms of the distributions. So let's take a look down here, for example. So if we look at the distribution in Z between 0 and 60 centimeters, you can see that they're pretty much flat, except for at the edges where they start to fall off. Yeah, dangers and advantages of non-linear correlation coefficients. I think the more you investigate the data, the more information you have. So I think you could potentially benefit from doing both kinds and seeing what you see. You can also maybe more directly take a look at the effect of changing your input data set, your list of input variables directly, and see how that affects your machine learning performance. There are also, I guess I'll make a comment, there are other cases where of machine learning where having multiple strongly correlated variables can really throw off what the machine learning does. For example, if you do clustering, that's where you try and get a bunch of events. You try and find patterns in the data where some events are nearby each other in some sense in your variable space. And if you have a bunch of correlated variables, then that set of variables becomes very important. It becomes overemphasized in this clustering step. So, looking at these correlations can be a quick way to just say, oh, maybe I don't want to include all of these highly correlated variables for something like clustering. But it depends on your application. You just have to investigate and see what you see. Okay, so let's move on to the next step. So I'm going to sort of assume that people are familiar with the concept of train and test sets. Basically, you can always do perfectly well at identifying one specific set of training data because you can always just memorize the exact patterns of that training data. But that's not a very useful way to train your data set. So you want to see how well it performs, your machine learning performs on an independent set of data. So here we use some very useful, this is where sklearn really shines in my mind, is these sort of helper functions. For example, train test split. So this step, we just take the data, we turn it into a NumPy array called xunscaled, and we also get the class answers and turn that into an array. And then we call this train test split function. And you can see it splits x into x train and x test, and then it splits y into y train and y test. And we've explicitly told it 30% of the data should be in the test data. That's probably a little bit high compared to a lot of applications. They might make it smaller, 20 or even 10%. But the size of your train and test data sets will sort of depend on your application. Then there's also a couple of other things. We fix the random state. That means it's going to do this same split every time we run this notebook. But it does shuffle randomly. So it means the same way that before we shuffled the data, this is another step of shuffling the data, but it will always shuffle the data in the same way. And then there's this nice little function stratify, where if you give it the class labels, that's y, it will ensure that the train and test data events are representative of the overall class label distribution. So we made it 50-50, and that ensures that the train and test is also 50-50 split to the extent that it can be between background and signal, or tritium and DD. Then there's one last step here, which is performing some transformations on our data. So in particular, there's something called sklearn has called a standard scalar. And what this does is it just sets the mean of each of these input variables, these features, to 0, and the standard deviation to 1. And that can be particularly useful for neural net applications where if you don't do this, it might have to spend a little while learning the natural scale of the variables. So when it does this adjusting of its weights, it might have to spend many iterations figuring out, oh, everything related to S2 area is in this range, and everything related to Z position is in another range, so I need to make the weights related to one of them scaled by some factor. So this just takes care of this for you. Yeah, that's that. So we have questions on this train and test split. Okay, the energy is reconstructed based on the S1 and S2 areas. So it's a linear combination of S1 and S2 areas, and the ratio of the two depends on the details of your detector. What is the advantage of standard scalar versus min-max scalar? So min-max scalar, that would be potentially very sensitive to outliers in your data set. So if you have a data point that's really high in one variable, or sorry, if you have a data point that's very large in one variable relative to the others, potentially that could change your scaling in an unfavorable way. But I'm sure there are use cases where you might want to go with a min-max scalar if you really want to pay attention to those outliers. And maybe if someone could just make a reply with the Zoom link. Is there any way to see if your data are well shuffled? Oh, that's a good question. I'd have to think about it more. I'm basically look at the structure, the order of your data in some particular, some subset of data or some of your variables, but I don't know a quick way to just test for shuffling. I think the best way is you just ensure that it shuffles and then you don't worry about it. Okay, so I'm going to move on unless there are other pressing questions that get a lot of upvotes. So the next section, okay, let's actually do some machine learning. So the next section is on boosted decision trees. So I requested, or I guess I mentioned that I sort of assume as a prerequisite that people are familiar with boosted decision trees. Just very briefly, if you aren't, a single decision tree is basically a set of cuts on different variables. So for example, there's this common example of, is a home in San Francisco or New York, and the elevation of the home is very highly correlated with that, right? So you could make a cut on elevation. You could say, okay, if it's tall, if it's high up, then it's more likely to be in New York. So boosted decision tree is a series of a decision tree is a series of single cuts on variables. It's a greedy algorithm because at each step it chooses the cut that maximally separates your classes. And then there's some termination condition like the max depth that prevents it from growing until you've perfectly separated all your data. So that prevents what we call overtraining. Then the boosted decision tree algorithm takes these single decision trees, which are pretty limited, and then the way it goes beyond that limitation is by basically reweighting the data set to emphasize the events that it got incorrectly in previous iterations. So it's sort of an iterative approach, looking at the harder events to classify, or the ones that earlier trees didn't classify. Then at the end, the output is some weighted sum of the individual trees, which, because these trees represent cuts, you can think of them as actually a weighted sum of voxels in your feature space, so little pixels in n-dimensional space. And then your output now, because it's a weighted sum, is a continuous output. I think there's a question about scaling data. Common practice for physics would be standard scalar. I think there are many ways you could do that scaling. I would suggest that as a generic default, but it will potentially depend on your application. So now we're going to actually make a boosted decision tree. So the way sklearn structures this, they have something called an Adaboost classifier, which actually says you have some underlying symbol classifier. In our case, it's going to be a decision tree. So this guy here. And then there's a separate step, the Adaboosting step, that can be applied to actually many different kinds of base classifiers. And so that's the Adaboost classifier step. So we first make a decision tree. We say we don't want it deeper than 3. And we also want to stop splitting if there are only 10 samples or fewer at a given node, at a given point down the decision tree. And then we combine a bunch of them. We specifically say, let's take 100 of them. And then in these methods, one of the things that's great about using machine learning libraries is that it's just a single line to do the training. And it's usually called something like fit. So here you just say bdt.fit x and y. And you might notice something here. I actually use the unscaled data in this case. You could easily do either one. The reason for pedagogical purposes I leave it unscaled is because the boosted decision tree looks at the features independently, and it naturally looks at the range of each variable directly. So it's sort of it doesn't need to learn the ranges in the same way. But there would be no reason not to use the scaled version in a real application. Then once we've done this training, so you may have noticed that was quite fast. It only took a second, and we had something like 10,000 examples in this very simple 4-dimensional space. So now the next step is we take our boosted decision tree model and we make some predictions. So that's it's called decision function. Here I split it specifically into the DD and the tritium data so that we can see what the distributions of this output variable look like for those two cases. This is just a bunch of matplotlib code to make this plot. So these are the distributions of the boosted decision tree output for both training and testing. So you can see it goes from -1 to +1. And our DD, which is more signal-like, indeed is more positive. And our tritium is more negative. And there's a little bit of overlap sort of in the center here. And another thing that we can see right away is that the train and test data, those data points, are fairly close to each other. This is not the best way to judge if you're overtrained, but if the distributions between test and train were very different, that would be an indication that you're really focusing on the statistical fluctuations in the training data set specifically. And that's what we mean by being overtrained. Let's see, do we have more questions? The zigzag structure. So one of the things that's tough about machine learning is that often you don't, this output space is not very interpretable, and we'll have at least a couple of presentations later in the workshop discussing interpretability of machine learning algorithms. There's this very common objection to machine learning that it's a black box and therefore can't be trusted. So I can't tell you what the explanation is for this particular structure in the data, but we could actually start investigating it. We could see, for example, if we took a cut between 0.55 and 1, if we looked at this hump here and we started to visualize it in some of our input data spaces, say S1 versus S2, maybe we'd be able to figure out what those populations were and investigate them a little bit more. I haven't done that, so I don't actually know what the answer is, though, in this particular case. But I do highly encourage that general type of thinking of what is the structure of the information that the machine learning algorithm is learning, and how does that map onto our data space, and can we learn something physical and human interpretable from it. What is the most universal way to balance sets, classes with BDTs or other machine learning algorithms? So it depends on what you mean by balance. I think it's pretty much standard to have your class, for example, signal and background classes, to be equally weighted in your training and testing set. And then after you've done this training, that basically gives it the best chance to distinguish between the two. After you've done the training, you can have it optimize. You can have it set the cut on its output to heavily be biased towards one end of the spectrum or the other. Basically, do you care more about false positives or false negatives? I don't know if anyone else on the call has any comments on that question of balancing sets. Are there use cases where you might not want the signal and background to be equally weighted? I guess when I say people on the call, I'm talking about our other organizers.
I think that's a common trick to, like, if you don't have signal and background equal ratios, then amplifying the backgrounds in the training is something, well, I haven't seen it much in physics, but it's in a lot of other machine learning applications. I forget what there's some jargon for it.
Right, so we'll also talk about weighting our data set in a section here. And you can reweight your data set if it starts out unbalanced to make it balanced. But I think typically, I don't know an example off the top of my head where you don't want your classes to be balanced. Okay, so now we want to go to the step of judging the performance. And we're going to use something called an ROC curve. I hate the name, stands for receiver operating characteristic. It's from back in the day when people were, I don't know, learning about how to make radios or sonar work or something. But the point is that it's a plot of your true positive rate, that is signal efficiency, versus your false positive rate, that's your background leakage. So sometimes, depending on who's drawing it, these variables may be switched around a little bit. You may have one minus one of these variables instead, so you flip the axis. But essentially, it tells you if you make a cut on this output variable, so you make a vertical line and you move it along here, as you move that cut, what fraction of the signal and what fraction of the background are you getting correctly, and what fraction are you missing? So sklearn has a very nice function called ROC curve that'll just do that for you. You just give it the true labels, and then you give it the predictions, and then it'll make this curve for you. And I want to point out, as with many of these sklearn functions, you don't have to have, in this case, the boosted decision tree is a sklearn object. But if you got these predictions from any other object, like TensorFlow, neural net, or something like that, you can still apply this same function. And in fact, I think sklearn is kind of the common way to do these ROC curves. So now we can see what our particular classifier looks like. So perfect classification would mean that you could get to the very upper left corner. So 0 background leakage and 100% signal efficiency. Random guessing would be a diagonal line. I also drew, just to guide the eye, the line of constant signal over square root background. In rare event searches, that sort of, it is a simple proxy for the line of equal sensitivity if you have a background model and you're expecting very few signal events. We're doing much better than that simple, than having no cut in that simple metric. We're way up here. But I also want to say that this is a fairly simple case, so we can get pretty good performance. And often, if we're looking for very rare events, this may or may not be the case for your application, but if you're looking for very rare events, you really don't care so much about a big chunk of this plot. You really only care about the very low background leakage parts of the plot. So for that, we maybe want to highlight specifically the low background leakage part by taking the log of the x-axis here. So this is really the space that we'd be more focused on. We can see that, for example, at say 90% signal efficiency, we have somewhere between 10 to the minus 2 and 10 to the minus 1 background leakage. And we could sort of tune based on our specific application, whether we really, do we need to be in the 10 to the minus 3 range of background leakage? And is it okay if we lose about half of our signal? In a lot of cases, it would be perfectly fine to make a hard cut like that. Yeah, okay, so we have a question about hyperparameter tuning. So I'm gonna defer that until later, and we're gonna talk about what is hyperparameter tuning and cross-validation. But absolutely, we just sort of guessed, oh, let's have 100 trees to begin with. And in principle, the optimal number of trees, the optimal depth, all of these other things that you can set before you do the training, those are what we call hyperparameters. Those can be optimized in another way. So we'll get to that more later. The ROC curve, does the machine learning algorithm also have some way of optimizing background leakage and signal acceptance? So the machine learning algorithm will optimize one specific metric. In the case of the boosted decision tree, it's trying to optimize, it's sort of optimizing something called the Gini index. So something like the purity of the data set after cuts. In neural nets, you can set what it's, exactly what it's trying to optimize. It's usually something like mean square error of the predicted response versus the true label. So I guess that is what sets the optimization of the training. In terms of optimizing where, if you choose to take the application of to use as your final application, making a cut on your output, then where you set that point is something that you need to optimize for your particular application. So you could make something that would automatically optimize that for you, but it's not part of the machine learning training, I guess is what I would say. And then we also want to take a closer look at this question I brought up before, which is overtraining. So remember, overtraining is the case, if you're overtrained, you're really focusing on the statistical fluctuations of your training data set. So in this particular simple case of a boosted decision tree, there's something called staged predict, which will show at different stages of boosting, meaning different numbers of trees, what its prediction would have been. And you can do this, you can calculate the accuracy, for example, at different stages. And you can compare the training data set and the testing data set. And what we see here is this shows accuracy versus boosting stage. We can see that the training data set pretty much always is more accurate than the testing data set. And that's what we expect, because the training data set is the set of flashcards that we give it to learn the structure. So it's gonna tend to memorize that structure better than when we give it new examples, the test examples. But we can see that they actually, in this particular case, they tend to track each other reasonably well. So even until the end of the boosting, the test data set performance isn't decreasing. There will be many cases where you might continue to make a machine learning algorithm more and more complex. And so, for example, you train over more boosting stages, or if you're using a neural net, you train over more epochs, and the training will continue, the training performance will continue to improve, but the testing performance will actually either level off or will actually start coming back down. And that will really be a pretty clear indication that you're overtrained. And you want to either have cut off your training, it's a very simple way to address overtraining, or you want to do something called regularization or some other method to try and reduce the complexity of your machine learning algorithm, or handle this case of overtraining. There's a question, why is there a jump at 40 and no jump before? Looks like a phase transition happens between 10 to 40. Yeah, you know, sometimes, so the way this training actually happens is it's a stochastic process. I have no idea why it jumps at around 40. It's found some new pattern that's particularly relevant for the data around that boosting stage. And, you know, that sometimes these things happen when you have a random process. I can't comment on the meaning of that. So we're about an hour in to the tutorial. We have 2 hours total, which is kind of a long time for me to be sitting and talking and for you to be focusing on something. So I'm going to suggest that we just take a 5-minute break. If you want to put more questions in Slido, please feel free to. And let's say in about, it's kind of an awkward time, let's say at 9:10, so a little more than 5 minutes, we'll come back. Okay, great. So I love the question about dark matter coffee. We had some person ask, how much better does the ROC curve performance have to be to make the cut? So I guess I would say if you're in the case of a background or a rare event search, you generally expect your sensitivity to improve if you're anywhere to the upper left of this dashed line. So it's probably worth making the cut if you're somewhere over there. And if you want to decide where you want to make the cut, so where along this curve do you want to be, one simple way to optimize your performance is to look at which point in this ROC curve maximizes your signal over square root of background. But so that's a simple metric. It won't necessarily get you the perfectly optimal case. You probably want to spend a little bit of time exploring your particular application. Okay. Let's see. So, Chloe, are you there?
Yes, I'm just uploading the poll right now.
Oh, great, perfect. So I was hoping to get a little bit of audience feedback on whether do we want to spend more time specifically on me going through the tutorial step by step like we've been doing, or do we want to allow people to do some of the exercises at the end and play with the code themselves? And I and Reed can help answer questions. So that's going to be a poll. I'll check back and see the results of that soon as people answer it. Okay, but in the meantime, I'll keep going. I'll keep doing what I was doing. Right. So we just did the check for overtraining, and I would say we could probably have stopped boosting by boosting stage 50. Whether we're really overtraining, whether that's really a problem or not, it seems like probably it's not, because the performance on the test data set is pretty flat there. But there's also not much benefit to continuing to train. So we probably don't need more than maybe 50 trees in this particular case. There's also the question of, so this is looking at the specific metric of accuracy. And I don't really like that metric personally. What it means is if you make a cut at specifically 0, what fraction of the time do you get the answer correct? So if it's a background, did you predict it as a background? And if it's a signal, did you predict it as a signal? So that is only one point on the ROC curve. And it's kind of noisy as a result of that. And it's maybe not where you want to be optimizing anyway. You may care most about the true accuracy of your algorithm, but you may actually care most about this region over here where you have very low background leakage. The choice, so accuracy is basically picking one particular point along the ROC curve. It's not necessarily what you care about most. Another thing you can do, another metric for performance you can do is called the ROC AUC, or area under the curve. It's exactly what it sounds like. It's just the integral of this guy here. The maximum is 1. If we do that, if we show that performance versus boosting stage, training versus testing, it shows a very similar pattern. It's basically smoother. So I like it a little bit better than accuracy in that it's maybe more comprehensive. It's less sensitive to whether you're exactly on that cut at 0 or not. But you would maybe benefit from, instead of choosing that cut, instead of choosing the RC area under the curve, actually finding what particular point maybe you want to consider the background leakage at 50% signal efficiency would be another metric that might be important for your particular application. And you could make that a custom metric and really look at the performance in that metric. That might be what you care about. So the thing that you want to focus on is maybe specific to your particular application. Okay, so far, got 24 responses to the poll. We're about 3/4 wanting more step-by-step tutorial time, 1/4 for exercises, questions. Let's leave that open just a little bit longer. Hey, Chris, can I see the questions from this?
There are no more questions.
Oh, there are no questions. Okay. All right. Let's keep moving. Okay, so now one thing that I really like and I think is important, if possible, is to try and learn what information your machine learning algorithm is picking up on. So in this case, we're going to do this for the boosted decision tree with something called variable ranking. Variable ranking is something that, in this case, it's sort of looking at what variables are used to make specific cuts. And the variables that are cut on more often and that provide more improvement to this discrimination are weighted more highly. With neural nets, you don't have exactly the same algorithm, but you can still, there are other methods of looking at the importances of specific variables. And in particular, if you're looking at something like a convolutional neural network, you can look at these activation maps, which tell you what specific neurons are firing for different examples. And that can tell you information about what the algorithm is doing. So in this case, we see that by far the log10 S2 area is the most important, followed by S1 area. And then there's a little bit of information also in the position. And that's not surprising. If we go all the way back up to our input data, we can see that, you know, naively, if you just did a cut on log10 S2 area, that would do decently well at separating out these example cases, this example data set. Another thing we can do is we can see what is the boosted, we can visualize that boosted decision tree output in some subset of our feature space. So to visualize it nicely, we kind of want it to be in 2 dimensions or even 1 dimension. So we're not, it's important to remember this isn't showing the full structure of the data set. That's why we're using machine learning in the first case. But we can apply it to this particular case And we can see that it's sort of saying, you know, the further down you are in S2 area and the further to the right you are in S1 area, the more likely you are to be signal, that is a DD event, so yellow. You can actually kind of see a little bit of the structure of where the cuts are in the boosted decision trees by looking at this. But basically, this is just giving you a little bit of intuition about what information the algorithm is picking up on. Okay, looks like we don't have any other questions. And then, what are the? Let's see. Poll results. It looks like 70-30. Okay, so I'm gonna focus on more of the step-by-step tutorial time, and you are definitely encouraged to do the exercises on your own at the end. We may or may not have very much time for it. We probably won't have a lot of time for the exercises. Yeah. Okay, so now we can also, for this case of a decision tree, we can look at what individual decision trees in the boosted decision tree are doing. I'm not going to go step by step through the code that makes this. Essentially, there's an easy way to make a simple version of it, which is this guy down here, and there's a slightly more complicated version to make the nicer looking plot. But if we just take a quick look at it, we can see that the first, so this is only a single decision tree. It's not explaining everything, but the first thing makes a cut below 3 in this log 10 S2 area. And then the second thing is it makes a cut at 2.9 in log 10 S2 area. So it's looking at a tiny, if we're in this branch to the right here, it's looking at a tiny slice of the data between right at around 3 and about 3.1. So it's looking over here. And then the next thing it says is the S1 area less than 10? So it's sort of looking at this chunk and it's saying, okay, if it's off here to the left, then it's probably tritium, it's probably background. And if it's in that same chunk and if it's off to the right, then it's probably signal, it's probably DD. And if you actually look, the structure of this very simple example, the first tree in the boosted decision tree is only looking at log 10 S2 area and S1 area. Those are the only variables that it pays attention to. So it makes sense that those are the ones that get the highest ranking over here. Then there's some comments on how to make those plots. And then one of the last steps is, you know, once you've done your training of your model, you want to be able to apply it to other cases. So for this simple sklearn version, you can save it as a pickle file, is an example of how you can do it. And this code shows you what you do to do that. And then later on, you can read it back in with this code right here. Okay. Let's see. So do we have any other questions at the moment? Not seeing questions. Show Q&A. Okay. Yeah. All right, so I will move on. So the next step, this is something that I think is really not discussed enough, which is reweighting your training data set. So you can apply reweighting. Basically, what reweighting does is it helps you tell your machine learning algorithm what kind of data to be looking for in the future. So it's telling you what's the data set that we're really trying to optimize on. So this particular case, we're talking about separating tritium and DD calibration events. But if what we really want to know is how well can we separate WIMP dark matter from our backgrounds, that's not really the same question. And in particular, it's important that these two calibration data sets kind of have slightly different energy ranges. So maybe a better question is something like, how do we distinguish electron recoils from nuclear recoils in our detector data with only the information that the detector will have? So for example, for a fixed size of an S1 pulse, which is what we actually, one of the things that we actually detect, how easy is it for us to distinguish the two? So what we're going to do to make our data set more representative of that is we're going to try and reweight the training set so that we get flat distributions in S1. So that's much closer to asking this question of, at a fixed S1 size that's sort of the same for our two data sets, how well can we distinguish the two? So first thing I do is I apply a cut on S1. You can't reweight data in a region where there's no data to begin with. So no matter how you try and upweight 0, it's always going to be 0. So I restrict the range to only the set where we have a decent amount of data in both cases. Then the next thing I do is this is a simple way of doing reweighting. I do a histogram of the data in S1, and then I'm not going to go through all of the code in detail, but essentially the weight is some scaling factor divided by the area of those histogram bins. And what we see is this is the distribution of our training data set before reweighting. Looks pretty flat for the ER, and it's much stronger at low S1 size for the NR. And then we can see after reweighting, it's flat and equal for both. And another thing, this addresses the question of unbalanced data sets. So after we do this cut in S1 area, this guy here, we can actually see the number of events in our two data sets, our two classes, is not the same. But because of the way we apply the reweighting, the total weight in the two data sets is the same. So that means that the algorithm is going to treat the two classes as equally important when it's trying to learn from them. And that's really the most important part. Now, if someone asked a question about really strongly imbalanced data sets. If you had a case where, the tritium events after the cut, there were only 10 events that passed the cuts, no amount of reweighting is going to allow you to get over that fact. You can reweight it so that those 10 events are very important relative to each of the events in the other data set, but 10 events is really not enough examples to learn the structure of the data from. So you are still, in some sense, limited by the statistics that you have for your training data. You can't just reweight and suddenly become not limited by statistics. Okay, someone says pickles are not stable over time. So there's probably a better way to save an sklearn model. So for Keras and XGBoost, they both have their own specific format that you can save in. I don't know if anyone on the call has a better suggestion for sklearn models or for a generic Python object. We can maybe answer that question offline too. And then someone asks, you're normalizing the two possible outputs according to S1 size. Did this reweight be requested according to the importance of that parameter? So I think the question is saying, why did we choose S1? So yeah, I actually don't know the answer to how pickles aren't stable over time, but does this reweight, so there's the question of why we chose the reweighting to be flat in S1 size, and that will depend on your application. I guess in this case, I'm thinking of the way you do the reweighting is basically deciding what the question you're trying to ask is. so if we're trying, so a common thing in these dark matter detectors is to say, for a fixed slice of S1, what's the leakage between the electron recoil and the nuclear recoil band? So I've basically made the problem somewhat comparable to that question of what is the leakage for a fixed S1 size. But you don't, yeah, the choice of how you want to do the flattening will depend on what your particular data set is. Okay, so now there's some code that basically regenerates the weighted data set. Because of the way that it's done, we have to go back to the original data frames and do some of these steps again. But essentially, it's taking this weight that we calculated from the histograms, and then it does this train test split again, but now it includes the weights as well. So the way that it splits the X and Y, the inputs and the class labels also matches the way that it splits the weights. And we also do the scaling step again. And then if we wanted to, we can also visualize the weighted data set. Here I have the marker size representing the weights. Some versions of the Seaborn package for plotting work well for this, and the one on Google Colab, it turns out, doesn't. So I made it in Matplotlib. But essentially, you can see if we take a look at our distributions. I was lazy. I didn't make the diagonal plots. But if we look at S2 space versus S1 space, you can see that the orange dots are smaller in weight at lower S1 size and larger in weight and higher S1 size, which is what we expect. So then we do the same thing. Now we create a decision tree, we make a boosted classifier, and then we fit it. This time we pass it the sample weights to the training algorithm. And I ran into an annoying issue, which I didn't realize before making this tutorial, which is that sklearn's Adaboost Classifier actually modifies the sample weights that you pass to it because it does this step of reweighting the data that it learns on. So actually, I tell it, make a copy of the training data, the training weights, so that you don't actually modify the object wtrain, which we end up using later on in the tutorial. So we do this again. We've trained the model on the weighted problem, and then we can, again, this is an exact copy of the code above, but now with weights. Now we can look at the distributions of the boosted decision tree output with weightings applied. And again, the train and test look somewhat similar. It looks like there's a little bit more overlap, and we can quantify that by looking at the ROC curve here. So this shows now the weighted problem that we just did, the orange versus the unweighted problem in blue. And we can see that for a fixed signal efficiency, we have a higher background leakage in the weighted problem. So what that means is that when we do this, fixing the S1 area or flattening in S1, we've created a harder problem, but probably a question that's a problem that's closer to what we really care about. Okay, I'm not seeing more questions. We can again plot the accuracy and ROC area versus time, and we have a pretty similar pattern again. The test performance is lower than the training performance, but it looks like there's actually not much penalty for continuing to train. And then we can again get the feature ranking. And we can see again, S2 area is the most important. And if we draw our output data colored by the boosted decision tree output, now with the examples, the size of the markers set by their weights, we can see that the structure actually looks pretty similar to what it was before. Sort of the bottom right part of the plot is most likely to be signal. The according to the data set. But it seems like maybe it's the output is, it could be a little bit more focused on just the S2 area than it was before. It looks like we can see some vertical bands here. Okay, so I want to pause here for a second for questions before we move on to neural nets. Yeah, so yeah, I would argue that this is probably more representative of our particular case. And so it's not that our boosted decision tree has learned the information more poorly. It's that we've chosen a harder problem, is the way that I would phrase it. It's more accurate to what we care about. Okay, so I want to emphasize that everything I did above, all of those steps, even though I took the example of an sklearn boosted decision tree, you can equally do them all with a different package like TensorFlow 2. And we're going to basically go through exactly the same steps now for the neural network. I, again, sort of assume that you are familiar with simple, fully connected network, also called a multi-layer perceptron. Basically, you have your inputs, you have your hidden layers, which are some weighted sum of the inputs after being and which are then passed through some activation function, and then you have some output layer. So now we go through the code that actually goes to set this up. So basically we have this import TensorFlow object. Google Colab is nice in that it's sort of designed with TensorFlow in mind to begin with. And we're going to create a particular model through the Keras API. Keras is a specific user-friendly way of making these neural nets. And we're going to make a specific object called sequential. Basically, anything that looks like this picture here is going to be a sequential neural network. And we define a function. This is just sort of a helper function so that the steps of building this network that we have something like this here are all, we can easily repeat them with just a single function call. But basically what this does is it creates this Keras object called sequential. It adds a dense layer, so dense just meaning it's fully connected. All of the inputs are connected to the next layer. We tell it how to initialize the weights. We say it's a random normal distribution, the mean of 0 and a standard deviation of 1. So here this sort of ties into what I said earlier, which is that it's nice to use this to scale our inputs so that they're sort of in the range of 0 to 1, because our weights will be in a similar range too. And then for each, this is structured so that you pass it a vector that tells it what is the shape of the network. So how many inputs, how many hidden layers, and in each hidden layer, what is the depth or what is the size of that hidden layer. So for each of these layers, in this case, it applies a tanh activation function. One of the things that I'd encourage you to do as an exercise is see what happens if you change that to something like a rectified linear output, ReLU. This is maybe a more common activation function for deep learning. And then it does this step of adding the next layer in the network. You can see that this looks pretty much the same as the dense function before. And then at the very end, it has a sigmoid activation function to get the answer, the final answer to be between 0 and 1. This step of compiling the model is very important. So one of the most important things here is that it sets what the loss function is. So this is exactly the function that it's trying to minimize. And in this case, it's the mean squared error. So we're saying we want to minimize the means, the squared error between the output of the neural network and the true label. Then there's the choice of optimizer. This is what actually does, which the stochastic gradient descent, the step of setting the weights in the neural network algorithm. And then also we can define some metrics for checking our performance during the training. Okay, so we run that, so we make sure that that definition exists, and then to create this model, we call neural network, and in this case, it's going to have our 4 inputs, the number of variables. Then it's going to be, the next layer is going to be 10 nodes, reducing to 3 and then to 1. And we can call model.summary to see, let me run that. Did that go? Let's try that again. Now you can see it tells you the number of trainable parameters. So how many free parameters are there to be optimized, and then what is the structure of it. Okay, do we have questions? Okay. Okay, so there's a question, what's the difference between dense and activation layers? So you actually can, in Keras, make the dense and activation part of a single function call. In this case, it's sort of separated out so that dense is what sets the, what weights are connected to the next layer, and activation is what applies this activation function. But in the picture here, dense and activation are sort of combined into a single, into this function. Is there a performance difference in binary classification using an MLP with 1 single output node compared to a model with 2 output nodes, 1 for each class? Yeah, that's a great question. So if you have a case where the output, you're trying to do binary classification, that means that your labels will always be either a 0 or a 1. So whether you choose to structure your output as a single node that's trying to match that 0 or 1, or this one hot output where if it's a 0, you make the first node 1, and if it's a 1, you make the second node 1 and the other one 0. Both of them contain the same information, and the output nodes in that second case, if you have two nodes, will be, they should be completely anti-correlated, because the information you're trying to pick up on is just this binary classification. So I would recommend, if you have the case of true binary classification, just use a single output node. It's just going to be a simpler network and easier for the learning to happen. But you do have cases where you have multi-class classification, where there's many different labels, and there it's quite common to have multiple output nodes that are related to essentially the probabilities of the different classes. So generic answer, if you're doing binary classification, have a single output. If you're doing multi-class classification, it's common to do multiple outputs. Okay, and then the next step, it's going to take a little while, so I'm starting it now. The next step, the same way for sklearn, we did model.fit to do the training. The function in Keras and TensorFlow has the exact same name. So here we pass it xtrain and ytrain. We're considering the weighted version of this problem, so we pass it the sample weights, and then we also tell it specifically what is the set of validation data, x-test, y-test, and the weights. And then we tell it a little bit of more information. We say, how many epochs do we train over? So that's basically how many iterations do we look through the data set to do this gradient descent step of optimizing the weights. And this is directly analogous to the number of trees in the boosted decision tree step. So the more epochs you have, the more you have the chance to learn the structure of the data and of the training data in finer detail, but the higher the risk of overtraining. And then we can see when we run this, what the output looks like. It's telling us what epoch we're currently at. It tells us how long it's taking. It tells us the loss. So that's the value of that mean squared error function applied to our data set. And here we sort of care most about the relative loss. How is that number changing over time? Then the accuracy and the ROC area under the curve. And then it does the same thing on the validation data set. And now we're done training. We can take a look at the decision function output. So this is sort of similar to what we were seeing with a boosted decision tree. Now I've made the y-axis logarithmic. And you can see that the output, even though there's still noticeable overlap between the two distributions, the vast majority of the events are either at 0 or at 1. And this is sort of a common feature of these neural nets that are optimized with mean square error optimization. Because you're really trying to say, if you're confident about an event, you really want it to be 1, because if it's the further away from 1 it is, the more it penalizes that error. Anyway, so this is a pretty common result for a simple dense neural network to have the results be strongly biased towards the edges. And the more you do the training, the more epochs you train over, the more this output space will tend to be biased or tend to be structured in that way. And then we can also do the same check for overtraining that we did before. So the same way we looked at the accuracy or area under the curve versus number of trees, we can look at that for the neural net versus epoch. And we can see that actually the training and testing cases are very, very similar, but the test performance is maybe just barely underperforming the train performance, which is again what we expect. But the model accuracy is pretty flat after only a few epochs, so we probably don't need to be training as long as we did. Let's see, we have a couple of okay. And then the accuracy metric is the same as the metric, the accuracy metric for the boosted decision tree. It's just doing a cut. In this case, the cut is applied at 0.5, and it's saying, if you apply a cut at 0.5, what fraction of the time does it correctly predict the answer? And we can do the same step, visualizing the output. Here you can see it's much more clearly separated into yellow dots or blue dots. So that's just visualizing this fact that things are focused towards +1 or towards 1 and 0. But again, similar structure to the output data. And then if you want to save the model, you can save it in this particular TensorFlow format, just using model.save. There's a little bit more information on the save formats. And then later on, if you want to take that model and read it back in, you can read it in with load model. I have an important note here, which is that in this case, the data set, I didn't explicitly call it out, but it used the scaled variables, which means, and that scaling isn't part of the network itself. It's sort of a pre-processing step. So if you want to apply this data set, if you want to apply this trained model later, you have to make sure that your variables are scaled in the same way. And then we can do a step here where we compare the two, the neural net and the boosted decision tree. And you can see in this ROC curve space, you can see that they're fairly similar. The neural net seems like it's doing a little bit better. But there's a very important caveat that I want to make here, which is that we're comparing two algorithms on the same test set. And in principle, you could imagine doing this with 10 algorithms, or many different choices of hyperparameters. And by chance, you might get one of these trained algorithms that appears to be doing better, but it is in fact only doing better on that specific test data set. So what we're actually doing by comparing more than one algorithm on the same test data set is we're kind of, if we're trying to optimize which algorithm to choose, we're kind of turning that test data set, which was statistically independent and we hadn't used to train, into a training data set itself of sorts. So we actually, if we really want to compare multiple algorithms or multiple choices of hyperparameter, we can't do this comparison directly, or else we're risking picking up on a statistical fluctuation. So at that point, the proper statistical thing to do is something called cross-validation. And there are multiple different ways of doing that, but essentially you train on some subset of your data, and then you gauge its performance on a different subset of the data, and then you do the same thing multiple times with different subsets or different partitions of the data. And that gives you a much better idea of your sensitivity to the statistical fluctuations of the data set. Mean square optimization exaggerates to 0 or 1. Is it a good thing? Not necessarily good or bad. It depends on what you're trying to do. So if at the end of the day, all you're doing is making a cut at 0, you don't really care so much about that structure. It's just a question of whether it's gotten the answer right or not. If you are taking the output and actually really looking at the shape, you're not just using a binary cut on the output, but you're, for example, doing a fit in this output space, then it could matter for you. In particular, the way you do the binning of the data, if you bin the data, could be more important if everything is really focused towards the edges. So it's a matter of how you apply. Oh, Igor's asking how come the area under the curve is better for the test set. I don't think that's true. Just looking at here, it looks a little bit lower to me. Igor, if you're on the call, you're welcome to unmute.
Right, so on my screen, I'm running in parallel. There is a substantial gap.
Oh.
Yeah, but I think, and some moderator already answered, I think it's possible, again, due to statistical fluctuations, it is possible that you, by chance, get better performance on some test set sometimes.
Right. Yeah, I think yeah, that's right. It's just a statistical fluctuation. And in general, if you were to, go back and rerun those cells, I think you would get a different result. So that's another thing that I didn't really highlight. There are some random there's some random parts of this training, in particular when it initializes the weights, that will make it so that each time you call this, you make this model, this neural network model, it will be initialized slightly differently and randomly. Sometimes that's what you want. Sometimes you want things to be completely repeatable. So if you want things to be completely repeatable, you want to make sure that you tell these random steps, you give them a fixed seed, so that it will always do the same thing. And I don't remember off the top of my head what exactly the function call is to do that, but it would probably be something like d equals 1. Kazu, I think you can unmute if you want to make a comment.
No, I don't have any comment. I was just I don't have any comment. I guess, well, okay, so maybe one comment. For mean squared optimization, acceleration to 0 or 1 is a good thing. Yeah, like Scott answered, yeah, that's up to the application. But it's true, like for sometimes you can struggle, right? Using the mean square because it steps is squared. So if you're very far away from the optimum, then you can get lost. In that case, linear, L1 error, linear error can also be helpful, or you can also combine those two things. It really depends on the application and also error surface that you're trying to optimize.
Okay, right. And then here's a question: how to choose the number of layers and neurons, and then especially in this Lex analysis case. So I would say a lot of people, in my experience, people starting out doing neural network training, at least in this simple case, focus a lot on this kind of question of how do you decide the architecture. And I think often the question of how you decide the architecture is a lot less important than questions like what is your choice of input variables and how do you set up the problem to begin with. But in general, the best way, and I think Kazu should comment on this because he has more experience than I do, but in general, the best way to choose things like that is through this automatic hyperparameter optimization that I didn't really get into, but essentially you do this you do this cross-validation step. So you train multiple algorithms multiple times, and you just automatically vary some of these things like the number of nodes and number of hidden layers, and you find which gives you the best result. I don't know, Kazu, do you have a more complete answer to that question of choosing the architecture of your neural network?
No, I think what you answered is a sophisticated one. I think if you're lazy, you can also start by judging whether you feel comfortable to train. I mean, it's fast enough. If it's too many layers, too many neurons, you will see it by yourself immediately. It's so slow. Then you don't want to even try it out because it takes very long time to figure it out. I use that very primitive intuition first to see if any solution emerges, and then maybe worry about more sophisticated method that you just described.
Yeah, that's a very good point. I would say in general, in machine learning, but also in any analysis, I like to start with simpler cases and see if I can just get them working in some regard. And then if they look like they're doing something at all reasonable, then I can try and make them more complex and see if I can improve the performance.
So another rule of thumb is if you see a lot of overfitting that is hard to generalize, then your network is probably too complex, too many parameters. You want to trim it down. And on the opposite, if you have no difference between training and test performance, then you can guess that making the network a little bit more complex is likely to give you a little bit better overall performance.
Yeah, that's a great point, Igor. And we didn't have time to talk about methods other than stopping training early to deal with overtraining. But with neural networks, there are things called regularization, methods called regularization that are very effective at taking an architecture that can in principle have many free parameters, so it's very complex, and reduce that complexity not through changing the architecture, but by changing the internals of the network. So two ways to do this are to add a penalty to the optimization term. That's what's usually called regularization. So that means if you have a bunch of network connections with high weights, that is in some sense equivalent to guessing wrong some of the time. So that's one way to simplify and to help prevent overtraining. Another way is to add what's called a dropout layer to your neural network. So you can visualize that as being, if we go back to this picture, as if some of these connections are essentially get randomly turned off. And that helps make the network more robust so that it has basically multiple pathways for information to travel through. Okay. Right, so we're pretty much at the end of the 2 hours. You're welcome to continue submitting questions if you wish. But essentially, I'll just say so that if you want to play with this on your own, please do so. You can find it on GitHub if you want to run it locally and save edits. There are a couple of other sections that describe specifically how to do cross-validation, and it turns out that cross-validation on a weighted problem is a little bit tricky. And then there's also, unfortunately, we didn't have time to go through it directly, but I very much encourage you to go through the section on boosted decision trees with this XGBoost algorithm. If you have an application where a boosted decision tree is relevant, XGBoost is basically just a little bit fancier and more performant package for making boosted decision trees. And then there's a nice example of hyperparameter optimization. In this case, it uses XGBoost, but in the exercises, I've suggested and put some hints for how you might do hyperparameter optimization using TensorFlow. All right, we're 2 hours in, so I think we all need a break. If we just look at the agenda, now we have scheduled a 30-minute break. So let's all reconvene at 10:30 Pacific time, so in a half hour.